Hi, welcome to the solution video for Quick Check 6. As always, we highly recommend you try this problem on your own first and give your best attempt at it. But if you did not fully get the problem, that's okay. Usually for like the induction problems, we want to really focus on just getting those mechanical steps done. So that's everything but the inductive step. So you can spend the bulk of your time focusing on that like creative algebraic part. And that's what I'll spend most of my time on in this solution. So our problem is we want to prove that the sum of the natural numbers up to n squared is actually equal to each individual natural number cubed and the sum of those, which is actually a really surprising fact. And notated at first. We want to make sure we use the fact that now we write the sum of the natural numbers is up to n is n times n plus 1 over 2. So to start off, we're just gonna define what these two definitions. So we're going to let P of n be the statement. And basically just get a list of what you're planning to prove, and which is this part up here. So I'm just gonna go ahead and copy that over. 0 plus 1 plus. Okay. And then we're gonna say we want to prove that P of n is true for all n. For all n is more to define what n is under, so we're just saying natural numbers by induction. And it's very important that I state this by induction at the end. Another way you can also write this is you say for all integers n greater or equal to 0. That's basically saying the same thing. We just want to make sure we define what values of n can be. Okay, so first off, now we can go, with that done, we can go over to a base case. And here, natural numbers start at 0. So we're just gonna go ahead and that would be the base case. We have P of 0. And we know that, okay, you have 0 squared equals 0 cubed. So P of 0 holds. Nothing really complicated there, just straight up say 0 equals 0. You don't need to simplify that and just say the base case holds. So now we're going to move on to the inductive hypothesis, which again, these steps may seem very mechanical and they very much are. There's not much thinking to them. You just really want to get focused on getting these steps like done quickly and without any mistakes. So like on exams, you spend the most of your time on the harder part. So I'm going to suppose that P of K is true for some arbitrary, and it's important that I state this fact that K is arbitrary K in our domain that we're focusing on, which is natural numbers. Okay. And then inductive step, which is where we'll spend most of our time in. Step will show P of K plus 1 holds. And this next step isn't required, but I highly recommend you write it down, especially when it's first starting out, and basically writing what the goal that we're trying to prove is. So our goal is to show that basically we're gonna show like this statement, but with 2k plus 1. So we're gonna have 0 plus 1 plus dot to dot plus k plus 1 squared is equal to each individual element squared. Okay. Right. So now we're gonna start off, and we're gonna do a bunch of algebraic steps. And let me go ahead and write them, do the basic ones first, and we can reason through what we need to do next. So obviously we can start with f0 cubed equals 0 cubed plus 1 cubed plus dot up to k plus 1 cubed. Okay. And when you're doing this inductive step, you always want to get whatever you're starting with into some form where you can use inductive hypothesis. Because every induction proof, you're gonna have to use induction hypothesis, and if you don't, it's most definitely incorrect. So where inductive hypothesis is basically this right here. So we're gonna try to get this into the form of what we had up there. So I think this might be a bit straightforward since we have the sum of the cubes up to k plus 1. Let's actually isolate the sum of the first k elements, each one cubed, plus 1 cubed, plus dot dot dot, plus k cubed, and we'll still have the plus k plus 1 cubed. And that's just associativity, and make sure you want to cite your steps each time. Right now, then we can use our inductive hypothesis, which we've written above, and that's going to be that we have 0 plus 1 plus up to k, that's equal to the squared, and again, we keep this part right here, and that's by the inductive hypothesis. Okay, so now we're gonna want to take advantage of the fact that we were given that the sum of these numbers is equal to, can be represented as n times n plus 1 over 2. So let's go ahead and substitute that in. So we have k plus 1 over 2. And remember that this was only formed for the sum of the numbers up to k. Then we're squaring that, we're gonna have to square everything, which I'll go ahead and put that around. And let's just go ahead and say by given equivalence. Okay, so now it may be a bit hard to see where we're going. So a lot of times when we reach a step like this where it's not really clear, like we use our inductive hypothesis, we use any of the givens, I like to kind of work backwards, as in kind of like see what my goal is and see like, okay, I have this, how can I get that to what I want it to be, just so that at the end I can prove that this holds. So go ahead and hopefully have enough space. Well, I'm not that great at this, as you can tell. OneNote's kind of weird, but we're gonna want to end up having show that k plus 1, all that squared. And if we have a bunch of steps in between, then we've shown that p of k plus 1 holds. And let's go ahead and use this given equivalence again. And doing that, we have that it's actually, so we have, instead of k, we have k plus 1. And this is just k plus 1, which is going to be k plus 2. Again, it's over 2. We have that squared. So that's the goal of what we're trying to do. And I'll just go ahead, write this. Reasoning. Okay. Okay, so what I like to look is like specific parts of the equation that I kind of want to isolate. So over here we see that, okay, this involves in the numerator like a k plus 1 and a k plus 2, and if you factor this power of 2 in, it's k plus 1 squared and k plus 2 squared. We see that, Okay, so up here, we currently have a k plus 1 squared, which is what we want. So I'm gonna go ahead and just isolate that outside, and we're going to have k plus 1 squared, and that's going to be, and it's going to go ahead and factor this out. So that's going to be k squared over 2 squared, which is just going to be 4. And then basically, we also factor that k plus 1 squared out, so that just becomes k plus 1. Okay, so again, reasoning, you can just say algebra or factoring. I'll just go ahead and say algebra. You want to make sure you check with the TAs and instructors if like they want to be more specific on the reasoning. But here I'll just go ahead and say algebra. Okay, so now we have this k plus 1 squared on the outside, which is the first step if we want. We also want a k plus 1 and over 2. So now that we have this set, let's focus our thoughts on like the square brackets containing these. So when we have this, that's kind of hard to work with. So let's just try to somehow combine these two together. So I think I'll go ahead and put the k plus, have these over a common denominator 4. So go ahead and multiply this up here by 4 over 4, and doing that gets us k squared over 4 plus, and then we're going to have 4k plus 1 over 4, and that's again by algebra. And simplifying this, we have k squared plus 4k plus 4, all that over 4. And this looks like something we can work with up here. That's just basic factoring, and this can actually be factored into, we have k plus 2 and k plus 2, but squared. And this, I'm going to put this as 2 squared, you'll see why in a second. And again, those just are by algebra. This is some space. Okay, and then now, okay, this looks almost exactly what we want. We'll just have to bring k plus 1 into the numerator, and we can just factor that power out. And that actually ends up getting over 2, and all that squared. And that's exactly what we have right there. So let's go ahead and just delete that out of the way. Then we'll bring this. And that's how we and we have proven that P of k plus 1 holds. So let's go ahead. You should always write a summary for this. A lot of times people tend to do all these steps and skip straight to conclusion, but you want to state that you have shown that P of k plus 1 holds. It may not be required. So thus, we have shown P of k plus 1 holds. So this may have been really hard to figure out just like first time looking at it, but the key points you want to take away from this step right here is that, okay, so we want to get into a form where we use inductive hypothesis, which we got right here. And at this point, we're kind of stuck. And when you get stuck like this, it's really hard to try to keep find ways to work forward to end up with what we want. Instead, it's a lot easier to work backwards. So start at our goal and use the given equivalents up here. And we saw this was a lot more manageable to work with, since we could kind of saw some similarities in these two forms to get to here. And all of this is just algebraic steps after you figure out kind of like the big like crux of the problem, it's just doing a bunch of algebra to get to the goal. So make sure you don't forget the conclusion, which is and then so we say this P of n holds for all and then natural numbers by induction. Basically, kind of what our inductive the original statement is. So that's kind of that's a pretty difficult induction problem. And again, no worries if you did not remember to figure out on your own. It actually took me a pretty long time to figure this out on my first try. So it is a difficult problem, but again, you just really want to get good practice at working on just getting the mechanical steps down so you spend most of your time on up here. Because especially on exam, this part right here is where you spend most of your time working on. So this concludes the end of the quick check solution. If you have any questions, feel free to post on Ed or stop by office hours. And I hope you have a great rest of your day.